In this class, we conclude our discussion on formulation of quantum mechanics. So let us summarize our discussions under the title Postulates of Quantum Mechanics. So whatever we have discussed in linear vector space, some key concepts in these discussions we can consider as essential postulates of quantum mechanics. So let us consider them one by one. Let's consider the first postulate. I call this as the state postulate. Associated with any isolated system, there is an abstract Hilbert space. The state of the system at any time t can be represented by a vector ket alpha t in the Hilbert space corresponding to the system. So this is the first postulate. So for every system, every physical system, we can think about an abstract Hilbert space. I will define what is a Hilbert space. So there is an abstract Hilbert space, and a state of the system is represented by an abstract vector in this Hilbert space. And this vector, we use Dirac notation for that. This is called ket alpha at the time t. And conversely, we can say any vector in the Hilbert space is a possible state of the system. Okay, if we consider an arbitrary, there is the Hilbert space of the system. If we consider an arbitrary vector from the Hilbert space, it's guaranteed that it will be, it corresponds to a particular state of the system. And this vector is called state vector, and the Hilbert space is called state space of the system. So state vector means these terms we alternatively use: state vector, ket vector, a vector in the Hilbert space. And Hilbert space and state space are the same. Okay, the space of all states, all possible states of the system. That is the Hilbert space of the system. So we can alternatively use the terms Hilbert space as well as state space. So this is the first postulate. Now let us consider some essential features in this first postulate. What is a Hilbert space? It's a complex vector space which is complete and in which inner product can be defined. We have already defined what is meant by a vector space. It should satisfy certain axioms regarding addition of vectors and scalar multiplication of vector by a vector, multiplication of a vector by a scalar. There are certain axioms for these two operations. So in general, so that's a vector space, and if it is defined over a field of scalars, which are a field of complex, if the field of scalars is a complex plane, then we call it complex vector space. Okay. Now this Hilbert space that we consider for quantum mechanical system, this Hilbert space is a complete space, and inner product can be defined in this space. We know what is meant by inner product. All vector spaces, in all vector spaces, inner product need not be defined. Those vector spaces in which inner product can be defined are usually called inner product space. Okay, and Hilbert space is inner product vector space. In addition, it should be complete. So what is meant by completeness of a vector space? The idea of completeness of a vector space is different from the idea of completeness of a set of vectors. Okay, a set of vectors is complete if the number of vectors in the set is equal to the dimension of the vector space. Okay, then this complete set of vectors can be used as a basis set for a vector space. For example, in a three-dimensional vector space, a complete set should contain three vectors, three linearly independent vectors. This can be used as a basis of the vector space. But completeness of a set of vectors is different from completeness of vector space. So what is meant by completeness of vector space? If every Cauchy sequence, a Cauchy sequence means convergent sequence, if every Cauchy sequence of elements belonging to a space converges to a limit which also belongs to that space, then that space is said to be complete. Okay, so if a convergent sequence of elements belonging to a space converges to a limit point which is also in that space, which also belongs to that space, then we say that the space is complete. I will give a few examples for this. And the dimension of the Hilbert space of a system, it can be finite as well as infinite dimensional. Okay, sometimes it can be finite, sometimes it can be infinite dimensional. We have already seen examples of these two in our discussions, so I am not elaborating on that. Consider an example of a Cauchy sequence, which means convergent sequence. Consider this sequence 1, 1 by 2, 1 by 3, 1 by 4, etc. Okay. Now this converges to the limit point. So the limit point of this sequence is 0. It's like 1 by n. As n goes to infinity, its limit point is 0. And another example, consider 1.9, 1.99, 1.999, etc. So here the limit point is, this converges to 2. So these are examples of Cauchy sequence or convergent sequence. So if all the elements in this sequence and the limit point also belong to the same space, then it's called a complete vector space. That is the idea. Now let's consider a counter example. Okay. Consider what is a divergent sequence. For example, if our familiar the integral sequence, integer sequence 1, 2, 3, 4, etc. This is a divergent sequence. It's not a Cauchy sequence. It's a divergent sequence. Okay, and let us consider a counter example for a vector space, which is an inner product space. Okay, inner product can be defined in this space, but it is not complete. Okay, so every vector space need not be inner product space. That is one thing. Every inner product space need not be Hilbert space. We need this additional condition that we can go like this. We can say a vector space we can define. Okay, there are two operations to be satisfied in a vector space. Addition of vectors and multiplication of a vector by a scalar. Addition of vectors should satisfy certain axioms. Scalar multiplication should satisfy certain axioms. Then we can call it a vector space. And if it is defined over a field of complex, the field is complex plane, it's a complex vector space. But there is an additional structure we give to a vector space, which is called inner product. Okay, inner product space. So all the vector spaces need not be inner product spaces. Okay, only if we can define inner product in a vector space can we call it an inner product space. Now every inner product space need not be a Hilbert space. Okay, there should be an additional condition that the space should be complete. Okay, so a complete inner product space is called a Hilbert space. So I am giving a counter example. Consider a space of rational numbers. Okay, it's an inner product space. It's a vector space, and it's an inner product space also. Okay, it's a real vector space, and it's an inner product space also. We can define inner product there, but it's not a complete space, because in a space of rational numbers we can construct a convergent sequence, a Cauchy sequence, such that that sequence can converge to any rational number. Consider this example, 1.41, 1.414, 1.4142, 1.41421, etc. Now this here, for this sequence, the limit point is, as you may guess, this limit point is square root of 2. Now square root of 2 is not a rational number, it's an irrational number. Okay, so this sequence converges to the limit point square root of 2, which is an irrational number, and this is not an element of the space of rational numbers. So the space of rational numbers is a vector space. It's also an inner product space. Okay, but it is not a Hilbert space. Okay, so this shows that there can be complex vector space. Now plus an extra condition, if you can define inner product, it's an inner product space. But all complex vector spaces are not inner product spaces. Now plus you define an additional condition that the vector space is complete. then it's a Hilbert space. So all inner product spaces need not be Hilbert spaces. So what is a Hilbert space? It's a complete inner product space, a complex vector space which is complete and in which inner product can be defined. That is Hilbert space. And also let us keep in mind that the completeness of a vector space is quite different from the completeness of a set of vectors. We know what is meant by completeness of a set of vectors. The number of vectors in the set should be equal to the dimension of the vector space, which means that any general vector in the vector space can be expressed as a linear combination of these complete set. That's why a complete set can be used as a basis set in a vector space. We have seen many examples. We know that eigenkets of a Hermitian operator form a complete set. Okay, so this completeness of a set of vectors is quite different from completeness of a vector space. So this is the idea of Hilbert space. The next idea regarding Hilbert space is that that of normalization of ket alpha, normalization of a general vector in the Hilbert space. Now ket alpha, a general vector in a Hilbert space, is a unit vector. Okay, this is called the normalization condition. So vectors in the Hilbert space are essentially unit vectors. It means that we are not interested in the magnitude of these vectors, we are interested only in their direction. Okay, so they are essentially unit vectors. And this idea that the vectors in the Hilbert space are unit vectors, their norm is 1. Norm means a generalization of the idea of the magnitude of a vector. So if norm is 1, such a vector is called a normalized vector, and this condition for normalization is called a normalization condition. So it can be defined in 2 ways. If the vectors in the Hilbert space are discrete vectors, then norm is defined like this. Inner product between 2 different vectors is Kronecker delta. Okay, so if alpha prime is equal to alpha, right hand side is 1. So norm is defined to the inner product is equal to 1. It means that the norm is 1. We know that the norm of a vector from our ordinary 3-dimensional vectors, we know that norm is defined as square root of inner product of a vector with itself, or scalar product of a vector with itself. So if the inner product of a vector with itself is 1, alpha prime equal to alpha, then this inner product is equal to 1, right? So you have Kronecker delta. Then we can say that the norm is 1. Okay, and this condition also includes orthogonality of 2 different vectors. If alpha prime is different from alpha, right hand side is 0. So this also shows that the vectors in the vector space are orthogonal to each other. So in that sense, this is an orthonormality condition. And if the vectors are continuous, then this inner product is equal to Dirac delta function. So for discrete vectors, inner product is equal to 1. Inner product of a vector with itself is 1. And if it is continuous, inner product of a vector with itself is Dirac delta function. So these are the 2 conditions for the normalization of a vector in the Hilbert space. Second postulate is, let us call it as operator postulate. Every physical quantity of the system is represented by a Hermitian operator acting on the state space of the system. The Hermitian operators act on the state vectors. We have already defined what is a Hermitian operator, what are the important properties of Hermitian operators. We know that its eigenvalues are real and eigenkets are orthogonal to each other. Okay, so every physical quantity of the system is represented by a Hermitian operator, and these operators act on the state vectors in the Hilbert space of the system. The converse is not true. Okay, we know that in the postulate of state space or state of a system, the converse is also true. Every possible vector in the Hilbert space of the system is a possible state of the system. But here the converse is not true. Every Hermitian operator acting on the state space of the system need not represent a physical quantity of the system. So that we have to keep in mind. And how do we construct Hermitian operator? Here it is given there is a method of constructing Hermitian operator. If a physical quantity has a classical counterpart, for example kinetic energy, momentum, or total energy, potential energy, in this sense position, momentum, etc. In this sense, if a physical quantity has a classical counterpart, that means if a physical quantity can be expressed as a function of position and momentum. In all the classical physical quantities, we can express as functions of position and momentum. So if a physical quantity can be expressed as a function of position and momentum, we can construct the Hermitian operator in a simple way. Just replace position by position operator, momentum by momentum operator. So that is given on the right side. A cap represent the Hermitian operator corresponding to physical quantity A. X cap represent the position operator. P cap represent the momentum operator. So what you have to do is, you just in the expression, classical expression of the physical quantity, you express it in terms of position and momentum, and then replace position by position operator and momentum by momentum operator. Right? That is the procedure. But there are some details involved. In some situations, we have to ensure that the operator that is constructed in this way it is a Hermitian operator. It need not be a Hermitian operator always. We have to ensure that the operator, if you take the dagger of the Hermitian conjugate of the operator, you should get the operator. That's a condition for a Hermitian operator. Or a dagger should be equal to A. So we have to ensure the Hermitian character of the operator. Sometimes we have to make some rearrangement of the terms, but this is the essential idea. First you express the classical quantity in terms of as a function of position and momentum, then replace position by position operator and momentum by momentum operator. That is the recipe for the construction of a Hermitian operator. Okay. Let's consider some more details of this postulate. Eigenkets of Hermitian operator as base kets. A Hermitian operator has a complete set of eigenkets which are mutually orthogonal. So these are the essential two properties of eigenkets of a Hermitian operator. They form a complete set. That means the dimension, the number of eigenkets is equal to the dimension of the vector space. And they are also mutually orthogonal. So they can be used as an orthonormal basis of the state space of the system, of the Hilbert space of the system. Now the completeness of eigenkets can be expressed in two ways. If the eigenkets form a discrete set, this is the condition, summation over A prime, ket A prime, bra vector A prime is equal to identity. We know that this is a projection operator. So some projection operator summed over all states is equal to identity. That is one way of expressing the completeness of eigenkets of a Hermitian operator. And if the eigenkets form continuous set, as in the case of eigenkets of position operator or eigenkets of momentum operator, in such cases, instead of summation, we have integration. That's all. And an operator, if we express in the basis of its own eigenkets, this is a structure. Operator A is equal to, I have not used the cap symbol for operators. So from the context, we can see it's an operator. So an operator on its own eigenkets, in the basis of its own eigenkets, can be expressed as operator A is equal to sum over A prime, eigenvalue A prime times ket A prime, bra vector A prime. So that is the structure of an operator expressed in its own eigenkets. And also consider this idea, superposition principle. A general ket in the Hilbert space of the system can be expressed as a linear combination of the complete set of eigenkets of the Hermitian operator corresponding to a physical quantity of the system. We know that for every physical quantity there is a Hermitian operator. We know that the eigenkets of a Hermitian operator form a complete set. Now a general ket in the Hilbert space of the system can be expressed as a linear combination of these eigenkets of the Hermitian operator. So it's mathematically expressed here. Ket alpha is a general ket in the Hilbert space of the system, and this ket A prime are eigenkets of a Hermitian operator. Okay, ket A prime, the set of ket A prime are the eigenkets of operator A, which is the Hermitian operator. Then this ket alpha you can expand as sum over A prime, ket A prime, bra vector L prime alpha. And this sum over A prime, ket A prime, bra vector A prime is identity from the completeness of eigenkets. So what we have done is we introduce an identity on the left side of ket alpha, and instead of identity we have used the completeness condition. And this inner product between A prime and alpha, this is a scalar. It's a component of ket alpha in the direction of A prime. We can use a symbol C A prime for that. So we can write it as summation over A prime C A prime times ket A prime. So it's just like some constant times ket A prime. Okay. So this C A prime can be called expansion coefficients. So this expression is just like in a three-dimensional vector space we express a vector A as axi plus ayj plus azk if you are using Cartesian coordinates, where ax, ay, az are the expansion coefficient, I, j, k are the basis vectors. So this equation sum over a prime c a prime times ket a prime. This is just like that. Okay, instead of ax, ay, az we have different c a prime. Instead of I, j, k we have different ket a prime. Okay, so this is called a superposition principle. A general ket can be expressed as a linear combination of basis kets, which are often the eigenkets of a Hermitian operator of the system, acting on the system. The third postulate is about commutation rules. So in the first postulate, we see how to represent state of a system by a vector in the Hilbert space. Then the second postulate, we have seen how to represent a physical quantity of the system by a Hermitian operator acting on the Hilbert space. Now in the third postulate, let's see how these Hermitian operators are constructed. Okay, so we know the way is to replace position. If it is this operator has a classical counterpart, express the classical quantity by as a function of position and momentum, and replace position by position operator, momentum by momentum operator. But then this position and momentum operator, or whatever be these operators, they should satisfy some commutation rules. What are these commutation rules? Heisenberg commutation rules between canonically conjugate operators, they are these three. Okay, this qi and qj, the qj and qk. I is used for square root of -1, so we are using other indices. So qj and qk represent position coordinates, or coordinates which are equivalent to position coordinates, generalized coordinates we can say. So commutator between qj and qk is 0, between pj and pk, generalized momentum components are 0. So commutator between two different components of position operator, two different components of momentum operator are 0. They commute with each other. But commutator between position operator component and momentum operator component is given by IH cross times delta jk, where j and k represent x, y, z, or 1, 2, 3. Okay. So what does it mean when j is not equal to k, right hand side is 0, right? We have a Kronecker delta on the right hand side. So if j is not equal to k, right hand side is 0. So two different components of position operator and momentum operator commute with each other, like x and y, x and py, x coordinate of position and y component of momentum, x component of position and y component of momentum, x and py, they commute with each other when j is not equal to k. But if j is equal to k, Kronecker delta is 1, then we get qj pk is equal to IH cross. For example, x comma px, j is equal to k is equal to x. So x comma px equal to IH cross, y comma py IH cross, z comma pz IH cross. Okay, so this single equation, the third equation, represent a large number of how many? I think 9 components. Okay, xpx then equal to IH cross. Similarly, we have xpy equal to 0, xpz equal to 0. In the same sense, we can talk about y. Start for y coordinate, we can have ypx, ypy, and ypz. For z coordinate, zpx, zpy, and z. So 9 relations are given by this single equation, this single compact equation. So if the position and momentum components are the same, they are non-commuting. X comma px IH cross, y comma py IH cross, z comma pz IH cross. On the other hand, if position and momentum components are different, then they commute with each other. So these are the Heisenberg commutation rules for canonically conjugate operators. These are generalized position and generalized momentum. Always they need not be position coordinate and momentum component. For example, this qj can be angular component, angular coordinate, like azimuthal angle phi, and then pk can be corresponding conjugate momentum. Okay, if qj is phi, pk can be angular. If qj is an angle, then pk will be angular momentum. So consider phi and Lz. Phi, azimuthal angle is measured around z axis, and if pk is the z component of angular momentum, there is a commutation rule between them. Phi comma Lz is IH cross. Okay, on the other hand, phi comma Lx, phi comma Ly will be 0. So they can be generalized coordinate. They need not be position coordinate and momentum, linear momentum always. They can be angular position coordinate, angular coordinate, and angular momentum. The other possibilities are also there. So in general, such canonically commutation rules between such canonically conjugate operators are called Heisenberg commutation rules, and they are given here. So this is our third postulate. What about operators with no classical counterpart? Okay. Operators with no classical counterpart are constructed from their specific commutation rules. So earlier we have seen a recipe for constructing a Hermitian operator for which there is a classical counterpart like a position, momentum, functions of position and momentum like potential energy, kinetic energy, angular momentum, etc. But what if there is no classical counterpart for an operator? Then they can be constructed from their specific commutation rules. An example is spin operator. There is no classical spin. There is no classical analog for spin. We know that spin doesn't mean the spinning of a particle about its own axis. It's nothing like that. It's some intrinsic angular momentum. Some angular momentum other than orbital angular momentum. Okay. So how do we construct spin operators? From there, the components, the commutation rules for spin operators, and these are the commutation rules for spin operators. Spin components Sj, Sk equal to IH cross times epsilon JKL SL, where this epsilon JKL is a Levi-Civita symbol, and here all JKL are represent XYZ. Again, I is square root of -1. Using this Levi-Civita symbol, a lot of relations between spin operator components can be expressed together. Okay, like for example, Sx, Sy is IH cross Sz. Two different components of spin operators are always non-commuting. Okay, and on the other hand, Sx will commute with Sx itself. Sx and Sy will be non-commuting. It is IH cross Sz. Similarly, Sx and Sz will be non-commuting. And if you take Sy will commute with Sy, but Sy will not commute with other two components. In this way, 9 relations are encoded. There will be 9 relations between Sx, Sy and Sz components if you take any two together. Such 9 relations are encoded in this single equation. So this is not different spin components are not canonically conjugate variables. Hence, these are not Heisenberg's commutation rules. Okay, so commutation rules need not always be Heisenberg commutation rules. Heisenberg commutation rules are only for canonically conjugate operators. Spin operators is different. They satisfy their own commutation rules. We know that two different spin components do not commute with each other. On the other hand, two different position components, two different linear momentum components commute with each other. Okay, so from these commutation rules of spin operators, we can construct the nature of spin operator in quantum mechanics. They don't have any classical analog. So the earlier recipe will not work here. We construct a spin operator with the idea that the components satisfy these commutation rules. So the point is that commutation rules are essential in the construction of an operator, of a Hermitian operator, whether they have a classical counterpart or not. In either case, we need commutation rules to properly construct Hermitian operators in quantum mechanics. So next postulate is about measurement. Next two postulates are about measurement. Postulate 4, eigenvalue as the outcome of measurement. The possible outcome of any single measurement of a physical quantity A in a general state ket alpha of the system is one of the eigenvalues A prime, set A prime. So it's like you can imagine it as A1, A2, A3, etc. or A prime 1, A prime 2, A prime 3, etc. So it will be one of the eigenvalues of the Hermitian operator A cap corresponding to that physical quantity. So I have used two notations for the physical quantity as well as the corresponding Hermitian operator. Consider a physical quantity A. Its corresponding Hermitian operator is A prime. A cap. The physical quantity is A. Hermitian operator is A cap. So sometimes in some textbooks this notation is used, but in some other textbooks simply A is used. So most of the time this A represents an operator. Okay. So the possible outcome of any single measurement of a physical quantity in a general state ket alpha of the system is one of the eigenvalues of the Hermitian operator corresponding to the physical quantity. This is the fourth postulate. And there is this idea, quantum collapse of the state. The state of the system immediately after the measurement of the physical quantity changes from the general state ket alpha to the eigenstate ket A prime of the operator A, where ket A prime is the eigenstate corresponding to the eigenvalue A prime obtained in the measurement. So in the measurement, suppose you get the eigenvalue A prime. Okay, then immediately after the measurement, the state of the system, initially it is in, we know that initially it is in ket alpha, in a general state. Now from this general state, it collapses to the corresponding eigenstate. What is corresponding eigenstate means? The eigenstate corresponding to the measured eigenvalue A prime. That is, it collapses from ket alpha to ket A prime. This is called quantum collapse of the state. Okay, so this is connected to the idea of fourth postulate. Eigenvalue as the outcome of an individual measurement. Postulate 5 is also related to measurement. In many books, postulate 4 and postulate 5 are always stated together. Let's consider them as two different postulates. Okay, anyway, the number of postulates is not important. So postulate 5 means probability of getting an eigenvalue as the outcome of a measurement. The probability of getting any eigenvalue A prime of the operator A cap when the physical quantity A is measured in the general state, ket alpha of the system is P of A prime. This means probability of getting A prime as the outcome of a single measurement. This is equal to, the probability is modulus square of inner product between A prime and alpha, between ket A prime and ket alpha. We know that this quantity, inner product between ket A prime and ket alpha, this quantity is the expansion coefficient of ket alpha in terms of the eigenkets of the operator. So let us use the symbol Ca prime for that. So this probability of getting a particular eigenvalue as the outcome of an individual measurement is modulus square of these expansion coefficients. Okay, so this is the expansion coefficients, and Ca prime, hence Ca prime are called probability amplitude. See, the square of Ca prime, modulus square of Ca prime, that is mod Ca prime square, gives the probability. Then simply Ca prime is called probability amplitude. Okay, the square of the probability amplitude gives the probability, and Ca prime, the expansion coefficients, are also called probability amplitude. Okay, so this is a postulate. Probability of getting a particular eigenvalue as an individual outcome of an individual measurement is given by this formula, modulus square of inner product between bra vector A prime and ket alpha. This bra vector A prime ket alpha is the component of ket alpha along the direction ket A prime. So the square of that component gives you probability. Hence that component Ca prime is called probability amplitude. And let us consider one more aspect, one more detail regarding this postulate 5. This is related to expectation value. The average of a large number of measurements of a physical quantity A in an ensemble of the system in a general normalized state ket alpha is the expectation value of the corresponding operator A cap. Okay. So earlier in postulate 4 we were talking about the outcome of a single measurement of a physical quantity in a particular state ket alpha, in a general state ket alpha of the system. Now suppose we make a large number of measurements of the physical quantity, maybe 100 trials. Then how do we make these 100 trials? A basic result in quantum mechanics is that when you make a measurement, the measurement disturbs the state of the system. Earlier when we were discussing Stern-Gerlach experiment, we have seen that experimental results show this. Measurement disturbs the state of the system. So when the system is in a state ket alpha, when you measure the physical quantity A, then the state changes. We know that the state changes from the general state, it collapses to the eigenket. Then how do we make a second measurement? Okay, so for making a large number of measurements, we should construct a large number of identical copies of the system in the same state. Okay, so if you want to make 100 trials of measurement of a physical quantity A, we should make 100 copies, identical copies of the system in the same state ket alpha. This collection of identical copies of a system in a same state is called an ensemble. Okay, so whenever we make a measurement in a system, in a quantum system, any quantum measurement is done over an ensemble of systems in the same state. Okay. So what is the average number of measurements? This is given by the expectation value, and this is the formula for the expectation value. The symbol, we use angular brackets for expectation value of an operator. In the formula, I have not used the cap symbol for operator, but understand that it's an operator. So what is the formula? The expectation value is equal to bra vector alpha operator A ket alpha. Okay, so it's something like a matrix element of operator A in between the state alpha. What is ket alpha? It is the general state of the system in which the physical quantity, we make 100 trials of measurement, and we are trying to take the average, and the average is given by this formula. Let us see if this formula gives the average value. So in this formula, instead of ket A, I can substitute this expression. That means an operator expressed in its own eigenkets will be like this: summation over A prime. A prime are the eigenvalues, ket A prime, bra vector A prime. This we have seen before. So we are expressing operator A in its own eigenkets. Okay. So this is equal to summation symbol I am taking outside, summation over eigenvalue A prime. What else? Bra vector alpha couples with this ket A prime, and this bra vector A prime couples with this ket alpha. Okay. Now we know that alpha A prime, inner product between alpha and A prime is actually, we can interchange the ket vector and bra vector. What you get is bra vector A prime ket alpha star, complex conjugate of in the same inner product with the order reversed. Bra vector A prime ket alpha star. Already we have bra vector A prime ket alpha here. This term is bra vector A prime ket alpha star. So combining them we can write as modulus square of bra vector A prime ket alpha. So expectation value I can write as summation over A prime eigenvalue A prime times this term mod square of A prime alpha. But in the previous postulate, in the same postulate, probability of getting an eigenvalue is given by this quantity. Okay, so we can write this as sum over A prime eigenvalue A prime times probability of getting the eigenvalue. I have written this in words here. Expectation value is equal to sum over all the eigenkets or all the eigenvalues. Eigenvalue times each eigenvalue times probability of getting that eigenvalue. Okay, so when we know that when you sum over a value times probability of getting that eigenvalue, we are going to get the average of the quantity, and that is the expectation value. Expectation value is the average of a large number of measurements. So what we have demonstrated here is this definition of expectation value essentially gives sum over eigenvalue times probability of getting each eigenvalue. In other words, it essentially gives the average of a large number of measurements. So this equation also gives the connection between expectation value and eigenvalue. Eigenvalue is the result of each individual measurement, outcome of each individual measurement. Expectation value is the result of a large number of average value of a large number of measurements. And they are connected by this formula. Expectation value is eigenvalue times probability of getting each eigenvalue. Okay. The last postulate is about the time evolution of a state. The time evolution of the state ket alpha at the time t of a system is given by the Schrodinger equation IH cross dou by dot t of ket alpha equal to h ket alpha, where h is the Hamiltonian operator of the system. So this is called time dependent Schrodinger equation. It's a partial differential equation, and this is we will see that this is a second order linear homogeneous partial differential equation, and this differential equation decides the time evolution of the given by the time evolution of the state is given by this differential equation. So this is also a postulate. Schrodinger equation cannot be derived from any first principles. This is a one of the postulates. So in our discussion on linear vector space so far, we have considered the first 5 postulates in different forms, but sixth postulate, this time evolution of the state, we have not considered so far. This is the content of the next unit, quantum dynamics. Okay, so all the 5 postulates that we have discussed in detail so far in this unit plus this sixth postulate of Schrodinger equation constitutes the essential basic postulates of quantum mechanics. And among these different postulates, for example, about the fifth postulate, sometimes that postulates in some books you can say that you can see that fifth postulate is given by it's given as okay, the total number of postulates can be 5 or 6. Sometimes, as I have told earlier, postulate 4 and 5 are together combined into a single one, single statement about measurement. So there is a progression in the logical structure of this postulate. In the first postulates, we define we talk about how to represent a state of a quantum system. In the second postulate, how to represent a physical quantity by an operator, Hermitian operator. In the third postulate, what is the rules of constructing this Hermitian operator? So these are the commutation rules. Fourth one, so once we have a state and then an operator, then what happens when operator acts on the state? That is the process of measurement. So what is the result of measurement? That is given by postulate 4 as well as postulate 5. Postulate 4 talks about the outcome of an individual measurement, which is an eigenvalue. Postulate 5 talks about what is the probability of getting a particular eigenvalue as the outcome of an individual measurement. Now this instead of stating this probability, that is mod square of that expansion coefficient is the probability. And instead of stating this probability as a postulate, in some books they give expectation value as a postulate. So whether we give expectation value as a postulate or probability as a postulate, from one we can logically construct the other. If you start with the postulate of probability, you can show that the expectation value defined in a particular way gives you the average of a large number of measurements, because that is equal to eigenvalue times probability of getting the eigenvalue. On the other hand, if you accept expectation value as a postulate, from the expansion of rewriting expectation value as probable eigenvalue times a quantity, that quantity you can identify as the probability of getting a particular eigenvalue. So one of them can be considered as a postulate, the other can be logically constructed from that. So as we were saying, postulate 4 and postulate 5 are about the outcome of measurement when an operator acts on a state vector. And lastly, postulate 6 is about the time evolution of a state vector, okay, given by Schrodinger equation. So this concludes our discussion on the formulation of quantum mechanics.